I'm Ron Heichman. I'll be presenting today about the control of quadrotor UAVs in formation. My advisor is Dr. Puneet Singla, and I'm based out of this institution, University of Baltimore. Let me start by telling you about what I'm actually going to convey to you today. I want to basically describe to you the motivation behind this project, why we did it, why it's important to, our society and our technology, how the actual project works from an engineering or physics standpoint, how we used this engineering or physics knowledge to control these quadrotors, the actual mathematical modeling that we used once we coded this into a computer program, and what kind of future research I'll have. So let me start by telling you a little bit about why this is important. Quadrotor UAVs are basically flying robots. So as opposed to the ground UAVs that sometimes the military uses, such as bomb disposal robots or underwater robots such as autonomous submarines, UAVs are flying robots. This makes them more complicated than ground robots because of the fact that they can move in 3 directions and rotate in 3 directions. That's something I'll cover later on. They have the adaptive capability, once they're controlled, to complete a preset objective. So let's say I tell the UAV, go pick up that object over there. That's the only instructions he needs to complete the objective, not avoid this tree or fly this high or go this fast. That's the wonderful thing about control. They are capable of imaging a large area because of these characteristics they have. Information monitoring, possibly in a military zone. Execution of offensive military maneuvers, such as bombing or missile runs, such as the kind of things that a Predator UAV does nowadays. Defensive escort of a manned vehicle. Bombers are slow vehicles, and usually they have F-16 or F-15 escorts. If you're able to unman this kind of escort, it makes it a lot safer. And last but not least, urban area patrol. This is one way to reduce crime by a significant amount, just because you can be everywhere at once without actually having to have anybody controlling this. So let me start by describing how we go about talking about quadrotors in their relation to our world. A quadrotor has a 3-dimensional location and 3-dimensional rotation. Every object in this room has a certain reference from the walls and the floor. This determines your 3-dimensional location. For example, my head is about, it's about 5 feet and I guess 4 inches above the floor, middle of my head, and it might be a couple feet from that wall and a couple feet from that wall. That locates my head. The direction I'm looking is different than the location. So I might be looking so and so degrees down, so and so degrees to the side, and so degrees, rotated about this axis. So these rotations depend on another reference point. So I have a rotation relative to this wall, which is this rotation. I have a rotation relative to the floor, which is this rotation. And I have a rotation relative to that other wall, which is this rotation. So it's 3 rotations, 3 locations. This is called the inertial reference frame because what we're comparing this to is not moving. That's why it's called inertial. The quadrotor, on the other hand, has a body frame, which is related to its two arms. Here's one arm. Here's the other. And the vector or direction perpendicular to these 2 arms. So these are actually moving. So you can relate the location of this arm and this vector to the whole body frame of this room. So I can say this is so-and-so degrees from the actual frame of this room. So this is what we use to describe where the actual quadrotor is moving. It's called a quadrotor or body frame. If we combine two body frames and the inertial frame, we can describe the location of two quadrotors by one position vector to the chief, which is the leader quadrotor in the formation, and one position vector to the deputy, which is the quadrotor following the chief. So as you notice, they both have these body reference frames. This is what two quadrotors in formation look like. You have the chief in front and the deputy in the back. And basically what happens is that there's a certain vector or direction in between them that says, okay, the deputy is this far back to the side, this far down, and this far back to the other side. And he's rotated so and so. This allows us to get a relative position. So I can then describe the deputy quadrotor based on where the chief quadrotor is. Using all of this knowledge, we can start to control these quadrotors. An example of a controlled maneuver is a circular orbit. This is a very easy maneuver to execute because all it takes is a certain predetermined physical state. It doesn't take any control, which is active. All you need to do is put the quadrotor at a certain radius for the circle that it has to go, give it a certain velocity and a certain tilt. This allows it to keep going in the circular orbit. So how do we do this? The actual thrust or force that the quadrotor experiences is always in the up direction relative to the quadrotor. So earlier I was talking about the quadrotor arms. As you notice, there are propellers on each arm. They can only push the quadrotor in this direction. So in order for the quadrotor to go to the side, he would have to rotate and thrust himself to the side. Because of this, we have to describe where this actual up direction points. So it changes direction because the quadrotor might be rotating like this, and then it will have a force in that direction. In order to do this, we use attitude matrices. An attitude matrix is basically a description of how much something is rotated relative to wherever you are. So I could make an attitude matrix for this keyboard, for example. And I could say I have one arm in this direction, one arm in this direction. If this keyboard is rotated something relative to this room. So these attitude matrices are used in our calculations to say where the force is going. This is a little bit of notation for the mathematical equations that will be coming up. These are the attitude matrices that I was talking about. This denotes something related to the deputy reference frame. This denotes a vector in a certain frame. And this denotes a cross product matrix, which is an operation that we use very often in these equations of motion. So, as I mentioned before, we use these attitude matrices, Newton's second law, which has the sum of the forces is the change at time rate of change of momentum, and the relation between torque and rotational acceleration to derive these equations of motion for one quadrotor. So we have a translational and rotational equations. Translational equations describe how the x, y, and z location of the quadrotor is changing. So how fast he's moving in every direction. Rotational equations describe how fast he's rotating in every direction. So this is for one quadrotor. Once we have one quadrotor, we can describe the relative position of two quadrotors using the relative equations of motion. These are derived based on a vector between two quadrotors in a certain reference frame. So rather than me saying, okay, this quadrotor is this far from the floor and walls of the room, and this quadrotor is this far from the floors and walls of the room, which locates the two quadrotors, I say, okay, the chief quadrotor is this far from the floor and walls of the room, but the deputy is this far from the chief quadrotor. So I relate the chief to the room, and then the deputy to the chief. So it's sort of like a chain. I go one by one. Once we do this, we can get relative acceleration. The relative acceleration describes how fast these two are moving away from each other. So, as you can see, mentioned earlier, cross-product matrices. This is a term related to the angular acceleration, angular velocity, and all of this basically makes up a differential equation that will help us describe how these two are separated distance-wise. Now, we want to actually focus on controlling this kind of motion. So, we use what's called a linear quadratic regulator. Linear quadratic regulator basically uses a linear version of these equations, which means they have no multiplication, just addition times constants. And we can then control the motion of these two relative to each other using the linear quadratic regulator. Since this is the form that those previous differential equations take, in the most basic way, we can say they approximately equal this, and then use this approximation to control the motion of the quadrotor every time step. Our future research will be implementing additional control schemes, such as sliding mode control, Lyapunov controllers, and analysis of stochastic processes. Currently, I'm working on another research project related to probabilistic processes, which are basically, I have this much probability of this happening, so on and so forth. It's related to the quadrotor because when you're measuring the position of the quadrotor from a certain camera, you can never know exactly where it is. There's always error because the camera has a certain resolution, and maybe the quadrotor moved by the time you measured it. So you use the fact that there's error in these measurements to control the position of the quadrotor better. So instead of knowing exactly where it is, you can only know about where it is. And because of this, you have to implement what are called stochastic controllers, which means that they are based on probability. So we will implement this, and also, once we have a working controller, we will control this UV in a virtual environment, and then once we have a working virtual version of the quadrotor, we will control it in the real Vicon environment, which is a motion tracking system in the lab, which means we'll have two real quadrotors following each other. These are my sources. And I'd like to acknowledge my advisor, Dr. Praneet Singla, Sean Crump Owens, CSTEP and its faculty, Reza Mandakan, which is a graduate student working in my lab, and also Thomas R. Leach, which is our lab director.